Welcome back to the first session of ITC. Please take your seats. We're excited to have the Diamond session of ITC this year, organized by Synopsys. It's entitled Driving Innovation in Test and SLM, Real-World Success Stories from Synopsys Partners. So I'm very happy to invite the session moderator, Kiran, who is the Executive Director at Synopsys. Kiran?
Thank you, Arvind. So good morning, everybody. So nice to see you all. So I'm Kiran. I manage the test products at Synopsys. An interesting anecdote, my first ITC was in 1997 in Washington, D.C. I guess many of you would have been there, and I was representing Sunrise Test at that time. Sunrise was known for sequential ATPG and partial scan. And interestingly, at that ITC, there was a panel, is partial scan dead? And I said, what? I'm here at Sunrise. I'm promoting sequential ATPG, and then there's this panel on partial scan. So after that, of course, as you all know, combinational ATPG became the norm, and the rest is history. So today we're going to talk about all the innovations in test and SLM, and we have our partner customers sharing their real-world stories. And then we'll also give you a brief overview of what we do at Synopsys. So I have an esteemed lineup of speakers. I'll introduce them later. But before that, I guess most of you know, Synopsys is the #1 EDA vendor out there. We are close to $9 billion in revenue, the trailing 12 months. We're also a leader in semiconductor IP. So we are leaders in interface IP. We have the PCIe, UCIe, the USB, and so on, including foundation IP, memories. And with the recent acquisition of Ansys, we're also #1 in simulation and multiphysics. And as you can see, we have close to 28,000 employees worldwide, and we have offices everywhere to serve our customers. So when it comes to the EDA full stack, we have solutions right from design capture through implementation, verification, of course, test and silicon lifecycle management, and then manufacturing. And the cool thing about the EDA stack is, we are AI infused throughout the flow. So AI in terms of automation, AI in terms of performance. For test, it's about test pattern reduction and so on. And we also are hyper-converged. So as you go through design implementation, we are physically aware for implementing DFT. If you're doing sign-off, you want to make sure that your patterns pass on the tester, they're power-aware, and so on. So there's a lot of hyper-convergence between the solutions that impact test and silicon lifecycle management. With the recent acquisition of Ansys, we can offer solutions that have a multiplying effect. So as you know, the world is going towards AI and multi-die and chiplets and so on. So with that, of course, your IR drop is essential. Your thermal effects are essential. So with the combination of Synopsys and Ansys solutions, we can offer solutions for your high-value problems. And stay tuned and come and check us out at the booth, and we can offer you more information. So our test products are pretty much represented with our TestMax product family. So we have solutions right at RTL, which is the spyglass technology to do your RTL analysis, followed by design implementation through design compiler or fusion compiler, followed by pattern generation, diagnostics, pattern translation, X-tolerant logic BIST for automotive applications or safety applications. And then, of course, we have our memory BIST, as well as we have a unique IP called HSAT, which is for high-speed access tests through your functional protocols like PCIe and USB. So many of our speakers that follow me will talk about all these different technologies and how they've applied it in the real-world applications. Apart from that, of course, memory BIST is something that's unique. Arvind will be very happy. We want to recognize 25 years of our star memory system. And Synopsys acquired Virage Logic many years ago, but this particular technology now celebrates 25 years, and here's a brief video of our customers talking about,
best efficiency in repair, and the best granularity in diagnosis.
Having a flexible IP, like the SMS and the tools that come with it, has been essential to our success.
Together, we have delivered cutting-edge mobile and automotive solutions designed to elevate performance and quality.
Thank you all for those who represented us in the video. Followed by Memory Best, we have our leading line of silicon lifecycle management solutions. So we monitor your designs using our path margin monitors, PVT sensors, and then we can transport that information and then analyze that information and then act upon it. So as you can see in today's designs, SLM is becoming very prevalent, and we have talks about how our customers are using our monitor IPs to detect issues in their designs and so on. And then last but not the least, I would like to introduce our speakers. Our first speaker is Leon Stock. Leon Stock is the Vice President of IBM's EDA group, leading design and verification for IBM supercomputers and quantum systems. He'll be followed by Max Wu. Max is the CPU DFT manager at MediaTek in Taiwan. He has come all the way from Taiwan. He has over 17 years of experience in DFT, logic-based, JTAG, and ATPG. After Max will be Sajjad Pagarkar. Sajjad is based in the Bay Area, or I think local, San Diego. He is the semiconductor executive with 26 years experience leading end-to-end development and manufacturing of mobile and AI chips. At Google, he directs the full silicon engineering lifecycle and was instrumental in the productization of Google's Tensor SoC. Followed by Sajjad is Rakesh Kinger, also from Google. So he's the senior DFT productization manager with over 25 years of experience in DFT implementation, test, and manufacturing. And after Rakesh is Amit Pandey from Amazon. Amit is based in Austin, and he's the principal engineer at AWS, leading DFX architecture for AI ML chips. And last but not the least is Jean Van from Singapore, all the way from Marvell, Singapore. She is a principal engineer at Marvell, specializing in data management and process development for high-volume manufacturing. So as you can see, we have lined up these esteemed speakers to talk about right from RTL, shift lefting from RTL, using compression, implementing design for test, going through your system-level test, high-speed access test with protocols, and then production analytics. So again, I would like to welcome Leon as the first speaker. Thank you very much.
I hope you can hear me well. It is great to be at ITC again. I think Järvand invited me in 2019. At that time I was talking about quantum. I was looking at the program this morning. I did not see too many quantum test papers yet. So I think there's opportunity. There's real systems coming out there. So today I will talk a lot more about stuff that's closer to home, correct? Our systems that we are building and what we do with our systems. I mean, if you came here by plane this morning, if you paid your hotel by credit card, if you made a phone transaction, you probably ran your transaction through one of our mainframes, correct? These machines still run the world economy. Yeah, they run the governments, they run the airlines, they run the financial industry. So reliability is utmost important, correct? 8 nines. I mean, test people know what that means, correct? That's 1 hour in 11,400 years, I think, yeah, of downtime, correct? So these things don't go down, yeah? So when we design them, really being able to test them, be able to do a lot of pre-active, proactive maintenance, monitor these systems is of utmost importance. Also, yeah, with the introduction of our TLN2 processor that within our recent Z17 systems, yeah, we can run about 25 billion encrypted transactions per day, correct? That is more than Google searches, Facebook's posts, and tweets combined in a single day on one machine, right? Yeah, on one fully populated machine. So one of the things, we took the DPU, which is traditionally sitting kind of on top of the rack, we actually brought that to the other side of the PCIe, really put it on chip to accommodate, yeah, this huge amount of extra I/O on the chip itself, reduced power significantly, reduced latency significantly. Yeah, another big trend that you hear everywhere, everybody wants to do AI, correct? So our clients want to do AI in transaction. You swipe your credit card in under 10 milliseconds, they want to know if it's right or not to let the transaction through, correct? You make a complex financial transaction, that moves a lot of money across different countries, Somebody wants to score that to make sure that it is likely to be a transaction that's allowed to go through there, So we started to put a lot more AI acceleration on chip. But as you heard this morning as well, we are getting a lot more generative AI models, correct? That get bigger, put a lot of more stress on memory, on the memory footprint, on data that needs to move in and out. And we see our clients, they want to run quick models, correct, in transaction on the chip. They want to run way more sophisticated models, which they have a little bit higher latency, maybe a couple of seconds before they need to score that, but way more advanced kind of scoring algorithms. Insurance companies that try to detect fraud and so on, that will run on the kind of cards that we are allowed to plug in the systems. Right, so that's what we call kind of the two sides of AI that run on our mainframes. So for the second part, we made available the IBM Spire Accelerator card. So this is a PCIe test card that goes into the drawers inside the mainframe. We can put, I think, 48 of these. So brings significant amount of extra AI power to the actual transactions that are going on. But going back to the beginning, correct? These machines need to be incredibly reliable. So our clients put a premium on the reliability that we put in our systems. So our design for test, design for maintenance, design for proactive maintenance is at an utmost. So what have we started to find, correct? That when our designers focus on what we call the functional description, correct? That's the mainline logic that you see in the bottom left there. But then we ask them, hey, you need to do all this test insertion, correct? As a test community, correct? All the test fabric that needs to come in there. In addition, we said, hey, you need to do all this design for reliability, availability, and service. Basically, put a lot more IP connected up on the chip. Then a lot more, hey, design for security. There's a whole bunch of stuff in there. Design for easier debug, design for manufacturability, and so on. So what we found is that our logic design teams got totally overloaded. Right? We got what we called at that time, way too many cooks in the kitchen. Everybody wanted to basically get his or her thing into the RTL. Really brought our productivity down, created confusion, and probably created a couple of extra bugs that would have been unnecessary. So we took a step back, about 5-6 years ago, 7 years ago, I think by now, and said, hey, we need to do this differently, correct? Can we automatically insert all this content in the mainline RTL, correct? So we came up with a set of these content weavers, as we call them, that are kind of rule-based systems, that take your RTL and then add a lot of content to it in a completely automated fashion, correct? And the great thing is that we structured this as a rule-based set of content waivers. I mean, in hindsight, looking back now, is that this plugs really nicely in the agentic flows now, correct? Because the rule-based stuff actually gives you a guarantee that things kind of come out as predicted, which unfortunately all these agentic LLM systems don't have yet, but it also now, but if you plug them in as agents, kind of you get a little bit more flexibility in steering them in what you actually want to do, but you still get a sort of a pretty much guaranteed correct by construction out as long as you follow the rules in the rule-based systems. So we were quite successful in deploying this in our mainline, mainframe power systems flow, our main processor flows, because we own the kitchen. We basically provide the recipes, we own all the IP, we work very closely with the semiconductor foundry to basically give us a full end-to-end stack. And while doing that, we got tremendous benefits, correct? Increased productivity, correct? Mainline logic designers just write mainline logic, Everything else got inserted. We got a lot of faster simulation because we said all this stuff that automatically gets inserted, let's not simulate that all the time, correct? We just do it at the end, So focus simulation on the mainline logic. And the real thing, we got fewer bugs. yeah, because people had much fewer lines of codes to stare and get right. And of course, we had errors in our scripts, yeah, and in the automatic generations and in the weavers. But over time, they disappear and they don't reappear. Yeah? And that's the big thing. Once you get them right, they're right for the duration of the project and for the next 10 projects following it. So when we start to look at our other ASIC chips, yeah, we do chips for cryptography. I showed you one of the AI acceleration chips. We have a bunch of other chips for networking, for storage. We said, hey, basically, can we mimic this type of weaver methodology for these chips as well, correct? And get the same type of shift-left advantages, yeah, faster runtimes, get good hierarchical tests, and so on. Yeah. Unfortunately, for these chips, we don't own the whole kitchen, correct? We get IP from memory providers. Yeah, we get IP from all type of other providers. Yeah. Kind of follow some more of the rule book that the foundry provides us versus asking for all type of exceptions, right? So our own approach, which worked very well in our kind of setup for our processors, yeah, is can we replicate some of the benefits, yeah, in a more industry standard setting? So we started to work with kind of the TestMax team, and we found out that actually they shared a lot of the ideas and the values, correct? Let's help integrate DFT along the design, correct? Automate it as much as you can, correct? Enable really early validation in the process, yeah? If you get it inserted right, yeah, it will stay there, correct? And if you can do it before PD, yeah, you have way less disturbance throughout the PD process of all the things that otherwise get added in because of the test purposes, yeah? In addition, yeah, we got a lot of stuff, I wouldn't say for free, but at least a really good head start on the memory BIST, correct? A really good head start on the compression. Yeah, we need a lot of help from the Synopsys services team for our first chip, correct, to get it right. We're doing a second chip that we're mostly doing it by ourselves. But helping this framework set up has really propelled, I would say, also the other chips forward, yeah, and start to realize some of the benefits that we have also seen in our microprocessor flows. So in general, I think the lessons we have learned is that, yeah, all the additional aspects that you want to insert into your design, try to automate it as much as possible, right? Because that automation keeps you an enormous amount of reliability in the process, allows you to shift left significantly, and likely reduces a lot of bugs that you otherwise would introduce in your entire process. And the other thing is that, yeah, it's not only DFT, right? There's DFT, it's designed for reliability, availability, security. There are many other aspects that I think you can build on top of a framework that does this automatic insertion. So in general, I think we have been very happy kind of to replicate a lot of the merits that we have seen in our mainline processor flow for our ASICs. And thank you very much for your attention here.
Okay. Good morning, everyone. I'm Max. I'm the CPU Duty Manager from MediaTek. It's my pleasure to be here today to share with you how we improve in test efficiency using TestMax platform, stream fabric, and SEQ compression. I will cover MediaTek product lines, test changes, and how we scale our test infrastructure using with these technologies. I will also highlight key project results and discuss the future collaboration opportunities with Synopsys. Let's get started. Allow me to give you a quick introduction to MediaTek. MediaTek is the world's fifth largest fabless IC design company with 16.5 in revenue and 4.1 billion in R&D investment in 2024. Every year, our chip powered over 2 billion connected devices, and we have 21,000 employees worldwide. We are #1 in several key markets, including smartphone, smart TV, connectivity and networking, Chromebook and tablet, and smart home devices. In addition, We rapidly growing in automotive and ASIC solution. Okay, with such a diverse range of product lines, testing is quite challenging. So, on the right, you can see our comprehensive testing requirements, including the wafer final test, digital stress test, and the diagnosis and the failure analysis, system level test, and the in-field test. We need to guarantee the quality and the reliability for our customer. At the same time, we to deliver this product quickly and quickly. Yeah. So yeah, it's really a challenge. So in today's talk, I will focus on the stream fabric, and the SEQ to how we use highly test efficient short test to optimize our production flow. This slide shows how Synopsys scale the test using end-to-end test technologies. DLT provides a test compression architecture which can reduce the test data volume. This is especially beneficial for complex design with huge amount of test data. Unknown tolerance logic-based enable robust self-test, even in the presence of unknown values, increasing test coverage. Stream fabric is designed for high throughput testing, so we can move the huge amount of test data quickly. It lets us send the data in parallel to these multiple cores, and which is a big advantage for today's complex design, which has a lot of embedded blocks inside. SSAT, or high-speed access test, supports a fast, flexible access for wafer system level and in-field test through the interface like PCIe and USB. Okay, so with TestMate technologies, we can apply a user can apply the consistent and the scalable test solution across all stages, from manufacturer testing to system level testing, final to the in-field test. Okay, here we can see our scalable test architecture. I will focus on the stream fabric and the SEQ. As mentioned, SEQ is to reduce the test data volume. So here you can see we have many SEQ codecs here. So we need an efficient way to test all of them quickly. That's where stream fabric comes in. As mentioned, stream fabric is designed for high throughput and parallel testing. So we can deliver our test data to this codec at the same time, making it possible to test all of them in parallel instead of one by one. So this since the test resource and the I/O count are limited, we use the shared scan input and the single dedicated output architecture to increase the test bandwidth. Okay, so this architecture really simplifies our DFT planning and implementation. With standard interface, we can start our DFT planning at the early stage, and we can assign the codec pins straightforwardly and easily scale to a large number of codecs, a large number of codes. Okay, so by combining stream fabric and the SEQ, we can achieve an efficient and scalable test solution. On the left, you can see the HSAT, high-speed access interface. Function as is an interface. It can connect the external host, ATE, to the internal test architecture, so that we can run individual patterns through the USB interface. Okay, here is our key achievement from our project. Showing how much we improved from a SEQ-only design to the combined SEQ and SF design. Yeah, you can see the table here. The first column, we compare several main features. And the design one is our baseline. We use the SEQ only design. And the design two, we add the stream fabric to the SEQ. So we compare DFT architecture, scan IO pin number, stream fabric ratio, SEQ codecs, instance count, and the overall test cost. And what really impressed is that you can see that we use the same scan IO pin number with design 1 and design 2, but the design 2 is much larger and complex. It has over 100 SEQ codecs, and the instance count is over 3x higher than design 1. Despite of the big jump of the size of and the complex, we're still able to reduce the test cost from 1 down to 0.4. Okay, so this really demonstrates the efficiency and the scalability to the combined SEQ and the SF test solution. Okay, looking at the bottom, yeah, we boost our test throughput, and we still keep our test power friendly, and we enable the flexible test scheduling. The most important is that we reduce our test cost and apply the support the efficiency testing through the whole silicon life cycle. Okay, finally, we're looking forward to new opportunity with Synopsys through the TestMax platform. We are looking to the further improvement in test quality and the in-field test quality, especially in ADAS, hyperscaler, and AI applications. And another key area is that leveraging the TestMax unified NDM database for improving the productivity. Yeah, it helps us to simplify the handover process between the synthesis, DFT, and backend teams. We also see the great potential in shared scan-out architecture, support for ATPG quality of result and the scalability. And we are also focused on low-power ATPG QOR improvement for test cost reduction. Okay, finally, we are exploring AI technology to further optimize our mass production flow. Okay, that's all. Thank you.
Good morning, everyone. Can we start slide? Yeah. So I'm not going to talk about Google. I'm not going to talk about our products or something. I'm going to talk about some good collaborative work we have done with Synopsys. Yeah. So, and I'm going to tell you why this is the innovation needed for us as an industry to carry forward when we go towards, especially towards chiplets, we go towards more advanced nodes. This is the probably future I look at. So, very first thing, I'm going to use mobile as a platform, but you can take it to any chip. In my humble opinion, I guess mobile SoC is the most complex SoC one can build. Reason being, it features hundreds of IPs. It has clusters of CPUs, GPUs, TPUs, extensive multimedia, HSIOs, security engines, you name it, and then probably 2,000 plus clock domains, 100 plus power domains, and then you operate those in 20 plus DVSF, we call it dynamic voltage frequency scaling, at least 20, 25 different modes of operation from low voltage to high voltage. And on top of that, you also do adaptive voltage scaling so that you can save power. Right? So it becomes a very, very complex chip. And what's happening with us is, as an industry, if you look at this trend here, right, logic transistor density, in last few years, we have gone into millions. 20 years ago, the chip sizes were roughly 200 million, whole chip. Now we are talking about 200 million, 250 million transistors per square mm. That's a density we are looking at with this 3 nanometer, 2 nanometer, right? If you see the CPUs, right? Early 2010, 15, we were in 1 billion transistors per CPU. Right now, we're talking about roughly 50 billion transistors in CPU. Just a massive scale. Next, cost per transistors. The reason we are going in that direction because cost per transistor is going significantly lower. It was going fine until our COVID moment, I guess, right? COVID and AI came into picture, and then wafer prices slightly going higher. That's the reason I think we have kind of saturated at that point. The moral of the story is this is like we are putting too many circuits into smaller geometry, and it is kind of, from test perspective, it's an explosion of test content, all right? So we'll have to pack tons of tests into smaller test time because the cost of test is very, very important for all of us, right? You want to be able to test it thoroughly. You want to be able to get the DPPM what you want. For example, mobile SoCs are limited by less than 500 DPPM, but practically we are looking at 100 DPPM. And how are you going to get that? You do extensive testing. How do you do testing? You rely on your good DFT, good due diligence, all right? Structural testing is basically your foundation. And with these advanced nodes, you require advanced fault models. If you use advanced fault models, the test time grows. For every fault model, it is roughly 2 to 4x test time, right? Whatever you could take with the structure, typical traditional StuckCAD. So you just talk about this. If you're going to add these fault models, for example, cell aware or small delay defect or bridging or something, every model comes with some test time requirements. On top of that, Foundry also tells you to do some custom fault models, okay? So all in all, if we see now, all of a sudden we have a challenge of putting lots of test content, right? And lots of modes, by the way. We don't hardly talk about test modes. Most of us think that, okay, I'm just testing at one voltage, one frequency. It doesn't work that way. Nowadays, the way FinFETs are, you need to be able to test at least 5 to 6 different voltages, different frequencies to cover the whole span of your operation. So that explodes your test time, right? So all in all, we have a good challenge, and I guess that gives us job security also, right? Because our jobs depend on testing. So I'm very happy about this challenge right now. So what we have done with the Synopsys is we are using this their IP for high-speed I/O. Since most of the companies who are in this advanced node are already using SLT, by the way. It's not a question how everybody uses SLT. So let's stop asking why SLT. Let's start talking about how can we use SLT and what SLT can do for you. So what we are working on is right now we are pushing a lot of test content from ATE. We are making structural testing platform agnostic. Nobody's taking ATE away from it. So you do lots of testing at wafer level using ATEs, and then put all your, I would call insurance tests, we call it, or safety net tests, which are like a heavy hitters in test time from a memory base as well as structure. You put it on SLT. And this is what we have done with the Synopsys. And I'm going to invite my teammate Rakesh to talk about our implementation, how we have done the job. Thanks.
Thanks, Sajad. So in order to tackle the test challenges that Sajad just mentioned and take advantage of the test cost savings that the SLT platform offers, we were looking into all possible options that industry has to offer. Our criteria was very simple. Just like any DFT technology, we wanted this to be agnostics to our DFT tools that we use for insertion, verification, test pattern generation, diagnosis. We wanted it to be non-design intrusive because we didn't want to introduce too many test mode paths. We wanted it to use or reuse as much as functional mode protocol as possible. And DFT overhead and the timing overhead, we wanted it to be minimal. And above all, we wanted to make sure that all our test patterns that run on our tester platforms, we can take the same test patterns and port it onto the SRT platform. So that we were looking like almost like a zero overhead solution, that we don't have to regenerate any of those test patterns. Now, with this criteria into mind, the high-speed access test IP from Synopsys, this became a backbone of our solution. And Maxu covered briefly in his slides also that how they are using. And the main motivation for us was that this IP reuses pretty much the same protocol, the same functional mode protocol. So what it means is that similar to our mission mode path, which the USB interface uses, this IP sits with and interfaces with the AXI fabric and the scan fabric and the tap controller. So what it means is that using these GPIO pins, AT accesses this scan fabric and this tap network. Now, similarly, using this SSET IP, we can access the same network using this SSET IP. The entire RTL, timing constraints, verification test benches were automatically generated by the tool. So that once we are done with the integration, we could easily verify that all the connections are made in the design correctly before we see issues at a later stage. Now, important thing to note is we have another tool called TextMax ALE from Synopsys. What this tool does is it takes all our AT test patterns, our memory-based patterns, stuck-at, transition, advanced fault models, which we have already run on AT, and they're production-worthy. And it takes all those style patterns and converts it into USB packets. And now, instead of tester driving those USB packets, we have a host system which drives those packets and then receives and compares the output stimuli. So just like AT can mask specific cycles, our drivers sitting on the host system can mask those cycles. So pretty much you can envision that now we have given a new backdoor entry to all our AT test patterns, but using the USB interface. This IP supports both USB and PCIe, but we decided to use USB for this for our application. The other advantage is that now, if anything fails on our SRT system, we can diagnose it. TextMax ALE enables us to remap all our failures back to our test patterns, generates the similar format AT fail logs that we get from the tester. So using the same diagnosis infrastructure that we use to diagnose AT failures, now we can use it to diagnose any of the SRT failures. And once we know that these patterns are very effective on the SRT platform and they're catching real defects, we try to migrate those patterns onto our AT platform. And this is how we improve our DPPM, but in a very test cost-effective manner. So to summarize, SSET IP has enabled us to develop a unified workflow, which allows us to generate, validate, and diagnose all our patterns across all the platforms. And we are also looking into leveraging the same technology for system level, for our in-system test. And now, since we have access to all the sensors on our design through IGA-tag network, now which is accessible through SSAT, we can also effectively use it for our silicon lifecycle management. So now with this, I and Sajjad would like to wrap up our talk, but would like to acknowledge that this has been a very good collaboration between both companies, which has led to successful deployment of this new technology and also enabled the first pass silicon bring-up success. Thank you.
Thank you. First of all, thank you, Synopsys, for the opportunity to present. We've been a user of Synopsys Star Memory System for a long time now, and today my talk will be mainly focused on how we're using it in in-field applications. Before going into the exact applications and SMS, I would like to introduce a little bit of our product lines in AWS Annapurna, especially the custom chips that we've been building for over a decade now. So starting with the first chip called the AWS Nitro, which is a network performance enhancer, which is for virtualization, security, and offloading the CPU for some critical tasks. It's currently used in all AWS EC2 instances throughout the world. And secondly, the Graviton product line is a compute product line, CPU, ARM-based CPU product line. And today, it's one of the fastest growing compute instance in AWS cloud. Thirdly, the AWS Inferentia Trainium, which is for machine learning, it's a custom designed chip for training deep learning models in the cloud. And I'll talk a little bit more about some of the things that we've done in this space. And one thing common with all the product lines is actually we use the SMS star memory system throughout all the product lines. So let's start with the motivation of why we think, why is in-system test so important today? And we've heard a lot of that in the conference already for the past couple of days, the tutorials, and even today you'll hear. So on the AI space for us, I think it's important because training large AI models like the LLMs requires running thousands of chips in a cluster, and it can run for weeks and months. And there's a lot of stress on the hardware in terms of voltage, temperature. You're running at peak performance for a long period of time. And as a result, things we're seeing now, silent data corruption is one of the key things that we've been talking over the past many years with a lot of publications. And it's also one of the key things that we are seeing in our data centers. Similarly, silicon aging or degradation is another major thing that will cause, is causing failures that we're seeing. And infant mortality, obviously, is another factor. For all of this, I think there's more need for doing in-field testing and as well as diagnosis and getting visibility into the chip. And that takes us to the area of silicon lifecycle management, which for us is a critical thing, an area that we are looking in, and we will also talk about how the SMS technology that we're using is helping us get there. Some of the key aspects of silicon lifecycle management for us is be able to do silicon debug remotely. So we want to be able to see a failure, and then we want to be able to go log into a server that's could be very far away, and we want to do the debug. We want to see what's going on inside. We also want to do remotely be able to go to a server and check the performance and make sure that the system performance is tuned right, make sure we have the clocks running, we have the voltage that we need, and all of that to tune the performance of the system remotely. And also, ultimately, we want to minimize our data center downtimes. It means we want to maximize the uptime. We want to be able to quickly put the system back or take it off. We want to do quick debug in that respect. And obviously, last but not the least, reliability, availability, serviceability is a key area that we have to focus to make sure that all our systems are running as we want. And in this space, with partnering with Synopsys, the SMS and SLM technology that we've been using for the last many years has helped us to kind of cover some of this gap here. Now, I will talk specifically about memory test and SLM. So I think using like I mentioned in the beginning, using the Synopsys self-test and repair memory system has allowed us to go for memory test all the way from wafer, all the way to AT-SLT, and all the way to in-field. So basically for us, the key is we want to take the same kind of test features that we have and same sort of test modes and the test application, and we want to take it all the way from wafer all the way to in-field. And I'll talk a little bit more about how that is possible. So if you look a little bit deeper into the SMS, the architecture, traditionally we have a server, then there's a sub-server, so it's a hierarchical architecture with 1500 protocol going to the sub-server, and then we have hierarchical memories, wrappers embedded all over the chip. Now, in order to take this to the in-system or in-field applications, we have to be careful of how we control this interface for our in-field application. So if you look traditionally on the AT, we use JTAG, right, to access all our instruments. However, going into in-system, we want to use either SPI or PCIe. So in most of our servers, we have high-speed access through PCIe. So that's one of the areas, that's the key interface that we use to be able to access ultimately this network. And that's possible through, we do have a custom APB tab bridge that's more for SPI, but to utilize high speed, we also use this HSAT tab bridge, which there's been some mention of that already today. So with the HSAT, we can actually get complete access for the scan side, obviously, but also for the tap in order to access some of the instruments that are embedded, like even the SMS controllers. Now, I'll talk a little bit about how we are enabling that through a microcontroller that we have in our system, which is the key component that enables this sort of application. So the microcontroller that we have sitting in our card is used to boot, configure, and train interfaces, but we also use it for SLM applications. And basically what we do for in-field testing is we can initiate BIST using the microcontroller. We can do things like we can schedule dynamic allocation of memories for power dissipation issues. We can do repair, hard repair, soft repair. We can do algorithm selection. We can do margin adjustments. We can even do voltage smooths. And so we want to test marginality and things like that. Again, it's possible because when you have an APB or HSAT trap bridge embedded, you can get full control over SMS, debug, and diagnosis in field. So now in the next couple of slides, I'll show a quick example of how we utilize this infrastructure to do actually a real debug and debug case. So in field, we actually noticed that there was a case where we are seeing more than expected ECC errors on some of the workloads. And it's related to sort of voltage fluctuations and voltage droop. So when we look deeper, we found that certain columns, as shown here, it's kind of a flipped here, but showing that certain columns actually resulted in these failures. And ultimately, it was due to a circuit issue on the memory that's causing some of the slow discharge of a sense amp. But the key factor here is that after we debugged some of this, what we figured out is memory is actually repairable, so we can actually implement a repair mechanism to be able to fix this in field. So what we ended up doing is we actually used the SMS and through the tab bridge to be able to do a soft repair of this by accessing very low-level control into the memory, and we can swap the columns that are failing across the board. And after that, we basically rerun BIST and check that the Vmin that initially was elevated, we actually brought it down, and ultimately that's improving our power as well as performance in the system. And then we also saw that no ECC errors were seen after we implemented this patch. So it's kind of a software workaround in a way that applied in field to improve the performance. Now looking at some of the next generation and what we are looking basically on the AI space specifically, if you look into it, we have exponentially increasing amount of logic and memory in the AI hardware. We need more logic. We need more memory redundancy as well as logic redundancy, something we're looking at. Also need fault tolerance and resiliency in order to handle the complexity of the systems, right? So we also have designs that are very deep in hierarchy with fully abutted floor plans. So we need scalable solutions that can address such type of design hierarchies. We also need bigger need for in-field debug and diagnosis, as I already mentioned. And we also need to do that at scale across remote data centers. In that aspect, we are continuing to partner with Synopsys on the next generation technologies. In summary, I will say that the in-field and SLM both are very critical for maintaining the overall data center health for us. And using the Synopsys SMS solution, we are able to do comprehensive SRAM testing from wafer to in-field, like I showed. And also, we presented an example of how we could take some of the low-level features of the controller, SMS controller, to be able to improve the reliability and performance of some of our systems in field. And we hope in the next generation, of the SMS, we will leverage some of the advanced features, and we continue the partnership. Thank you.
Good morning, everyone. I'm Jean, a principal engineer from Marvell, Singapore. First off, I would like to thank Synopsys for inviting us to be part of ITC to share with you the Marvell experience today. So the topic of the day is delivering custom silicon at hyperspeed, specifically how we are accelerating data analysis in the space of NPI, new product introduction, as well as high volume manufacturing. Sorry. Let me share with you, first of all, how the Marvell mission looks like. In Marvell, we provide solutions that move, store, process, and secure the world's data faster and more reliably, be it powering cloud data centers, enabling 5G networks, or securing our enterprise infrastructure. Our technology is at the heart of how data move across the globe. This is not just a technical statement, it is a reflection of what we do. We also believe that execution is as critical as innovation, and execution is the key to our customers' successes. And therefore, we work side by side with our customers, listening closely, adapting quickly, and delivering the solutions that are reliable, agile, and tailored to their needs. Because in today's environment, speed and precision is important. It's equally important. At Marvell, we also advocate collaboration because we know that progress doesn't happen in isolation. It is built together with our customers, our partners, and our teams, and each of us play a critical role. That includes every one of us who is in this room today. It is also through this collaboration we are building the infrastructure that moves the world forward. And why are we doing this? Almost everyone in this room is doing work that creates data every day at alarming rate and increasingly. And it's not just about getting the data, it is about how we are using the data to tell the story to our customers. The customers could be your external customers, your team who works with you on the same project, because somebody is waiting on the story to work on for tomorrow. And this urgency, that sense of purpose, is what is driving us. And if it's not mentioned enough already, today product designs are more complicated than ever before. Packaging technologies are evolving rapidly, and the pace of NPI is also accelerating. And what does that mean for us? It means the expectation to deliver that story to our customer is much higher than before. From test program development, product qualification, variability analysis, to delivering that first sample to our customer. Every step now needs to be faster, sharper, and more reliable. It is no longer enough to be good. We have to be exceptional, and we have to be fast. How are we then responding to the challenges that we have just seen? We know that we can't do this alone. This is why Marvell is focused on identifying strategic partners to help us build a more secure and scalable platform for high-volume silicon analytics. Synopsys is a valued partner whom we have been working with closely and continuing to do that to advance our analytic capabilities. We are also partnering with OSATs to ensure the delivery of high quality data that we can trust. And this collaboration enables us to make faster, smarter decisions throughout the silicon manufacturing and test cycles, and ultimately driving faster time to market to enhance our competitive advantage. And how are we doing this? We are leveraging on silicon.da product genealogy feature that will allow us to integrate our manufacturing and test data into a common platform. And using a common tool across our processes, it gives us the ability to identify defects with high accuracy. And with the data at a glance, we can now provide feedback to our customers with high confidence, and we can also pinpoint where there are possible gaps and where we can place our resources. With the complex flow management, it also provides granular traceability. This allows us to drive continuous improvement efforts across our silicon manufacturing and test cycles with greater efficiency. This would not have been possible without the steadfast support from our OSATs too. They played critical roles in delivering robust quality data on time, each time, and every time for execution. The data is typically available within 2 hours after the test or manufacturing event has concluded. This enables us to have a near-time data review, especially important for our high-priority silicon. So what have we achieved so far? We have been engaged with Synopsys for over 5 years now, and we have successfully integrated 7 test stages and manufacturing stages data into the common platform that is fed by over 100 data flows that is coming from our OSATs. We have now around 300 users all across Marvell offices that is using the platform for the analysis work. This primarily was driven by the product and test engineering in high volume manufacturing. However, it has since expanded to include users from the MPI space, from our supply chain planning team, to our quality, finance, and as well as a U management team, just to mention a few. And we are continuing to engage in active conversation with our internal teams to help make that work simpler and more efficient. And all this, we are looking at about 600 products that are already loaded into Silicon Dash, and we have since processed more than 4 million tests and events for this position. And this number is looking to grow even faster in the next couple of years. So my key takeaway for today can be summarized in the following 5 points. First, when we align on standard practices and use a common tool, we create consistency. And this consistency leads to a more predictable and reliable yield management outcome. Second, by making a tool intuitive, easy to use, and encouraging early adoption, we are empowering our teams to access data timely, right whenever they need it. Third, with fast feedback loop that help us identify issues early, improve our product integrity, and enabling us to deliver high quality products to our customers. Fourth, our KPI traffic light dashboard isn't just a dashboard. It generates actionable reports that drive yield improvements, process optimization, and cost reduction. Last but not least, the power of integration. When we are able to bring all this together, standardization, accessibility, speed, and insight, we are able to unlock the ability to to make smarter decisions faster, and therefore achieving the operational excellence that we are seeking. And with this, I thank you for your time, and we at Marvell are excited to continue this journey with Synopsys on this journey of collaboration, because we believe that with collaboration, we can build better technology tomorrow. Thank you.
Thank you for all the great talks. Really very, very strong presentations, 5 very up-to-date topics to be covered by our esteemed speakers. On behalf of ITC, I'd like to thank Synopsys for being a Diamond sponsor. Diamond sponsor is not only financial contribution to ITC, but also content. You see the state-of-the-art content that we receive due to that Diamond contribution as well. We will not have question answers here. We'll do the question answers at the Synopsys booth at 12 o'clock. So the speakers will be available for you to answer to your questions at 12 o'clock in the booth. Meanwhile, I'd like to thank again Synopsys for being an important contributor to ITC, especially being one of the oldest, the second oldest exhibitor at Synopsys after MCC. This year is the 40th year that Synopsys exhibits at ITC. Thank you so much.